in this next example, we're going to look at a more complex process. This one only has two reactions that are happening, but we have a reactor, a separator, and a recycle stream, which is going to add a mixing point to our system. So we have a desired reaction, 2 C2H4s plus oxygen makes 2 C2H4O, and a side reaction, again a combustion reaction, C2H4 plus 3 oxygens makes 2 COs plus 2 H2O. Now, in this case, the feed to the reactor, so specifically to the reactor, is going to be 3 moles of C2H4 per mole of oxygen. The single pass conversion of C2H4 will be 20%. The yield for this needs to be 80% of C2H4, or 0.8 moles of C2H4O out of the reactor, okay, per mole of C2H4 consumed in the reactor. So this is specifically in the reactor, not the overall process. For a basis of 100 kilomoles per hour of feed to the reactor, we want to find the required flow rate of fresh feed. So let's look at this diagram for a moment. So we have some fresh feed being added and mixed with a recycle stream. Together, these will make 100 kilomoles per hour of something that is 75% C2H4 and 25% O2. These go into the reactor where it will exit with C2H4, O2, C2H4O, CO2, and H2O coming out, some combination of those. These then go to a separator that perfectly separates the streams out to raw materials, C2H4 and O2, or the product, C2H4O, or the waste materials, CO2 and H2O. So this is going to be the system that we want to analyze. And we want to find the required flow rate of fresh feed for this system. Let's begin by starting to set up our material balance table for this system here. So in this case, I'm going to have a basis that is 100 kilomole per hour to the reactor. That's going to be my fresh feed to the reactor. Now, my streams, I'm going to label these as fresh feed, reactor feed. I want A to be the desired product, B the waste stream, so I guess C comes out of the reactor. A is my primary product out of the reactor or separator. B is the waste product, and then R for my recycle stream. The materials that I'm going to be tracking are C2H4, O2, C2H4O, CO2, and H2O. Now I'm going to do all of these in kilomoles per hour. And so I can put a total on there. It's not particularly enlightening. But let's do these so that my fresh feed, I'm going to use N1 and N2 is the amount of the feed. And I have none of these product materials. And in the the reactor feed, I was told that there are 75 kilomoles per hour and 25 kilomoles per hour and nothing else. For C, I know it's going to be N1, N2, N3, N4, and N5. Now, because this is a perfect separator, I know that stream A, the primary product stream, is only going to contain C2H4O, and the C2H4O isn't going to go anyplace else. So therefore, it's going to contain N3 C2H4O and 0 of everything else. Similarly, B is only going to contain my waste gases. So it's going to contain N4 and N5, and my recycle stream will contain N1 and N2. And essentially, I've already sort of done the balances on the separator. So it's a little bit of a shortcut, but if you can use some logic early in the problem, you can save yourself some time. It isn't wrong to do it the other way. It just is a little bit more time consuming. So what about my degrees of freedom table? Well, I've got the reactor, I have the separator, I have the mixing point, and I have the overall system. If I do this using molecules, it doesn't really matter which way I do it, but it's a convenient thing to learn how to do. So I'm going to write the degree of freedom table using this. So I need to know the number of reactions and the number of variables for each little subsystem. And then I'm going to have material balances. I'm going to have sum of x's, and I'm going to have process specs. And those will add up to get me degrees of freedom. So for the reactor, I have two reactions that happen in there. For the number of variables, well, it streams R, F, and C. And so I have 1, 2, 3, 4, 5 variables. I can write 5 material balances on these molecules. Sum of x's, not really. I didn't define the total flow in that stream. And process specs, well, I was given 2 process specs, and they do specifically apply to the reactor. If you'll recall, I had single pass conversion of C2H4 is 0.20, and I had yield in the reactor equals 0.80 moles of C2H4O per mole of C2H4. Now this is a specified form of yield. It is not based on the limiting reactant. If one were to check, in this particular case, the limiting reactant is O2, but they defined the yield specifically in terms of C2H4, so we'll go with that. So I have 2 process specs, and so the degrees of freedom is 0. So I can go ahead and start writing balances and solve the reactor if I wish, but let's go ahead and complete our degree of freedom table. Let's look at the separator. Stream C goes in, A, B, and R come out. The number of reactions in the separator is 0. My number of variables is 1, 2, 3, 4, 5. And I can write 5 material balances, no sum of x's, and I have no process specs. So again, I have 0 degrees of freedom. The mixing point, F and R come in, RF comes out. So I have capital N1 and capital N2, lowercase n1, lowercase n2 as my unknowns. So I have 4 variables. I have 0 reactions. In this case, I only have 2 material balances that I can write. I have no sum of x's, I have no process specs, so I have 2 degrees of freedom. So that one is not going to be very successful for me as a starting point. The overall system, F comes in, A and B leave. So I have 1, 2, 3, 4, 5 variables. I have 2 reactions that happen within the system. I have 5 material balances I can write, no sum of x's, and no process specs that apply specifically to the overall system. These are both in the reactor. So that would introduce variables that are not defined for the overall system. So therefore, my degrees of freedom is 2. Again, not the best place to start. So I'm going to start by looking at balances on the reactor, and in particular, let me use those process specs. So the single pass conversion. Okay, that's 0.20, 75 kilomoles per hour exit or enter the system, N1 kilomoles per hour come out. So I can use this to solve for N1. And so N1 is 60 kilomoles of C2H4 per hour. Now the yield in this case is defined as 0.80 equals the moles of C2H4O that exit the reactor, which is N3, divided by the amount that could have been formed. Well, okay, actually, it's per mole of C2H4 that was actually consumed in the reactor. So this is a different kind of a yield. It's not the traditional. So always read the units very carefully. So the C2H4 that was consumed in the reactor is going to be 75 minus N1, which in this case we just found was 15. And so therefore N3 is 0.8 times 15 is equal to 12 kilomoles C2H4O per hour. So I found N1 and N3. Now let's move on to doing balances on the reactor. Now I can choose to do this as a molecule balance or an atom balance. I am rather arbitrarily going to choose to do an atom balance. I did my degree of freedom table based on a molecule balance. That doesn't limit me. I can do either one. I can even mix and match if I really wanted to. So let's write these balances. So on the reactor, let me switch pen color here. My atoms are C's, H's, and O's. All right, the reactor has RF as the feed and C as the exit. So carbon, I have 2 in C2H4. I have 2 that exit in C2H4, but I already know that that number is 60. I have 2 that exit in C2H4O, but I already know that number is 12, and I have N4. And so I can solve this for N4. Okay. On H's, I have 4 that enter with a C2H4, 4 that leave with C2H4, 4 that leave with C2H4O, and 2 that leave with the water. Okay. So I found N4, N5, I've got N1 and N3, so oxygen. Oxygen enters as oxygen, so 2 atoms per 25 moles. Leaves as 2N2 plus N3 plus 2N4 plus N5. I know N3, N4, and N5, so I can solve for N2 is 10 kilomoles O2 per hour. All right, so that's the reactor. I have the number of moles of each of those. I now need to find N1. So in order to find N1, well, I could move to the separator because it's also degrees of freedom of 0, but that doesn't involve capital N1 and N2, so that's not going to do me any good. So I chose to next look at the mixing point. Okay, the mixing point is streams F, R, F, and R. So and I can choose to do atoms or molecules, but there's not a reaction happening here. So molecules seems to be more convenient. Okay, so, and again, you can mix and match. And I only have 2 of these that I can do, so I'll do this for C2H4 and for O2. For C2H4, I have capital N1 plus little n1 equals 75. for O2, I have capital N2 plus little n2 equals 25. And based on this, I can find capital N1 is 15. And N2 is also 15. All right, I could use remaining balances to check my work. So now, what if someone asked us some follow-up questions? So question 1, if we want to produce 1,500 kilograms of C2H4O per hour, and we use the same setup, okay, how much fresh feed will be needed? Now this assumes that everything remains proportional. So it's a matter of scaling. So we're going to need the molecular weight of C2H4O because they've asked for mass, and that's 44.05. And let's just play the scaling game. So first of all, 1,500 kilograms of C2H4O per hour, 1 kilomole of C2H4O is 44.05 kilograms of C2H4O. And in the original problem, we had 12 kilomoles of C2H4O per hour corresponded to 15 kilomoles of C2H4 fed per hour. Therefore, 42.6 kilomoles of C2H4 per hour required in the fresh feed. Okay, how much oxygen? Well, turns out it's going to be exactly the same thing. We would just simply replace this with O2, and we would also have 42.6 kilomoles of O2 per hour required in the fresh feed. So I can use this, and so this is the advantage of using a defined basis. I solve the problem, and then I can just use scaling factors, okay? And these are my scaling factors. Any of my answers can be used as a ratio to adjust my answer. Now, next question. What is the overall conversion? Okay, so in this particular case, it's how much of the C2H4 is fed minus how much exits divided by how much is fed. In this particular case, I have an overall conversion of 100%. So this concludes our examples on multiple reactions in systems. I suggest that you do some follow-up practicing, watch additional videos, try some homework problems. But as we move to the next topic, combustion, we're going to see that we're going to keep adding to our skill set here. So we'll continue working on this as we look at the topic of combustion.